Hi, good evening. Can you please confirm if my audio is audible to you and is my screen visible?
Yes, sir, you are audible and screen is visible.
Okay, thanks a lot. So we'll just start then. We have already waited for 5 minutes. Okay, so welcome again for week number 5 of the problem solving session for the course on Introduction to Electrical Engineering from Professor Bhim Singh, IIT Delhi. So yeah, so we'll just jump ahead right into the problems. So in this week we are having um, problems, just the one problem on circuits, okay, and a set of 4 problems from real power, reactive power, power concepts, right? And the remaining will be from mostly two-port networks, okay. Okay, fine. So we will go ahead with the first problem. So the problem is the circuit shown in figure 10 is at steady state before the switch closes. So steady state means to understand that an inductor behaves as a short circuit while a capacitor behaves as an open circuit. Okay. So this is for an infinite time period. That means if you tell steady state, it means it has been there for a long time. Okay. So for t less than 0, it has been for steady state. That is from minus infinity to 0 time, right? That is the circuit is in steady state, wherein you can just short the inductor. The response of the circuit is a voltage V of t, right? V of t is the voltage across the 10 ohm resistor. Okay. So the question is find V of t for t more than 0. So at the instant the switch is going to close, how my response for V of t would look like? Okay, that is a question. Now the point is I of t is the current through the inductor, obviously. So we have been given 4 options. We just need to find out the correct one. Okay. Okay. So yeah. So how do we solve this? First thing is that we will analyze a circuit under steady state. Okay. So that is the first thing we are going to do, right? So let me take it in my lap and let me change over to pen. Okay. Okay. So under steady state, right? Your inductor behaves as a short circuit. Okay. While your capacitor is going to behave as an open circuit. Okay. So particularly in figure 10, if you look, right? So your figure 10, is going to get modified something like this 18 volts and then ten ohms. So this is again 10 ohms. Okay. And they have given this to be V of t. So you have 40 ohms. Okay. Under steady state means the switches, what? The switch is now open, right? Under steady state, that is before t equal to 0. So the switch is open, which means that after this, you do not have any circuit. Okay. So Inductor is anyway a short circuit under steady state, but since the switch is open, it doesn't make a difference. Okay, so this is the circuit under steady state, that is for t less than 0. Okay, this is a circuit. Now what is V of t? V of t, or I should tell V for t less than 0, right? Now you understand that it is just a simple resistive divider, right? So V of t is basically 18 volts getting split across the 10 ohm and 10 ohm, right? Which means that your V of t is going to be how much? V of t is going to be, so what is your V of t? V of t would be 18 into 10 ohm divided by 10 plus 10, right? Which would give you 9 volts. So this means that V for t less than 0 is equal to 9 volts. Okay. So before the switch was closed, we were having a constant voltage of 9 volts across the 10 ohms resistor, right? So the initial voltage is 9 volts. Okay. And there is another steady state that is obtained. So one steady state is your, right? One steady state is your t less than 0. Okay. That is minus infinity less than t less than or equal to 0. So this is one steady state. You have another steady state at t equal to infinity, right? That is after the switch closes, right? After the switch is closed, you have another steady state at infinite time period. So over there, what would the circuit look like? In that scenario, the circuit is going to get modified something like this. You have 18 volts, 10 ohms, again 10 ohms. You're taking V of t across this. You have 40 ohms, and the switch is closed. All right, the switch is closed, and then you have the inductor which would behave as a short circuit. Okay, so this is the equivalent circuit when the switch is closed. Okay. Okay. So at this period, what is the V of t? So during this period, what would be V of t? For V of infinity, we will call it, right? So what would be V of infinity during this period? So V of infinity is the voltage across a 10 ohm resistor. Right now, 10 and 40 are in parallel, correct? So your V of infinity is going to be 18 into 40 parallel to 10 divided by 10 plus 40 parallel to 10, correct? This is the voltage, that is V of infinity. All right. So how much are you getting with this? So 40 parallel to 10, getting 8 ohms. All right. So 8 divided by 10 plus 8, right? Which is nothing but 8 volts. So you understand that before the switch is closed, right? The voltage is actually 9 volts. Before the switch is closed, voltage is 9 volts. And after the switch is closed, the voltage is at infinite time period. The steady state voltage is 8 volts. So basically you were at 9 volts. From 9 volts, some transient is going to happen, and finally the voltage is going to settle at 8 volts. Okay. This is the first hint. That is, we calculated the voltages across both the steady states. That is, before the switch is closed and after the switch is closed, we have calculated. Okay. And we calculated the voltages. All right. So let me take a new slide over here. Uh, okay. So yeah, so we have now calculated two things, right? So one for minus infinity less than t less than or equal to 0. V of t is how much? 9 volts. And V for t tends to infinity. After switch is closed, 8 volts. So this was steady state before switch closes. This is steady state after the switch closes. So you understand that basically your V of t is going to go from 9 volts to 8 volts. That's it. Okay. There is just a transient that is going to happen, and your voltage is basically going from 9 volts to 8 volts. Okay. So now we are done with the first step. The next step that we would do is basically to compute the time constant. Okay. So the time constant is computed. Okay. So now the point is we are closing the switch. All right. So we are closing the switch at t equal to 0. At that instant, at the instant you close the switch, what is the time constant? Okay. So that would define the response of the circuit, right? That is, inductor is going to be there and the net effective resistance. The combination of that RL circuit would be giving your time constant. All right. So at the point the device is going to or the switch is going to close, right? We have to find the time constant. So which means that we have to find out the Thevenin resistance. Find out R Thevenin, okay, for time constant, right? So we just need to find out the R Thevenin. Okay. Okay. So if we want to find out R Thevenin, right? So what do we do? In order to find out the R Thevenin, first thing we do is disable the voltage source and the current source. That is, disable independent sources. So what you do is you basically disable independent sources. Okay. What do we mean by disable independent sources? Short voltage source and open the current source. Okay. If you short the voltage source, it means the effective voltage is going to be 0. If you open the current, no current flows, the current is 0. All right. Okay. So you have disabled independent sources. All right. So let's redraw the same circuit, disabling independent sources. All right. So 18 volts is now a short. So you have a short over here, and then you have the 10 ohm resistor. All right. So you're having 10 ohms. This is the node, right? That is across this only we want to find out the Thevenin resistance. And your switch is now closed, which means you have 40 ohms over here, and you have the inductor, which is 25 Henry. All right. And I want to find out the Thevenin resistance looking at this particular. Yeah. I want to find out the Thevenin resistance looking at this particular node, right? If I look from here, what is the Thevenin resistance? Okay, so what is the resistance? You understand that 10 and 10, right? So 10 and 10 are going to be in parallel. Okay, so RThevenin would be 10 and 10 in parallel in series with 40 ohms, which means you get 45 ohms, right? This is your RThevenin. So what is your time constant? Time constant is L by R, which is 25 over 45, or you can write this as 5 by 9. Yeah, 5 by 9 seconds. This is your time constant. Okay, L by R. All right. So we have found out the time constant. So we now have all these information. That is, we know what is we now know what is the voltage before switch closes at steady state, what is the voltage after the switch closes at steady state, and what is the time constant of the circuit. Okay, this is enough to write the response, right? So just imagine, okay, your voltage is basically going from 9 volts to 8 volts. Okay, that means that my voltage is basically decaying. It is decaying from 9 volts to 8 volts. Okay, so if I write the time expression, right, it will be having a constant number 8. Okay, I will be having a constant number 8, and over that there will be a decaying component which decays from 9 volts to 0. So um, so let's take a new slide. Okay, so I will just insert a new slide. Again, let's try to understand what's happening over here. That is, voltage was initially, right, that is at t less than 0, voltage was 9 volts, and t equal to infinity, voltage goes to 8 volts. So basically you understand that voltage decays from 9 volts to 8 volts. Okay, and how is it decaying? That is given by the time constant. That is, your time constant is 5 by 9 seconds, right? Time constant is, yeah, 5 by 9 seconds. So your time constant is going to be 5 by 9 seconds. Okay, so voltage decays from 9 volts to 8 volts with a particular time constant, which means that your response, right, V of t can be written as, so it has a constant number 8 because final voltage is going to be 8 only. Initially it is 9 volts. From 9 volts it's going to decay to 8, which means that I will be having a number 8 constant DC, right? And over that I should be having a decaying component, right? Over that I will have a decaying component that falls, right? So where is it falling from? The overall voltage is falling from 9 to 8, which means that the decaying component is falling from 1 volts to 0 volts. So you can understand that initially it would be 8 plus 1, 9 volts, and finally it will be 8 plus 0, 8 volts. Okay. So there is a decaying component that is falling from 1 volt to 0. That is 8 plus 1 would be 9 initially. And as it decays, the voltage will fall to 0, which means the total voltage will be 8 plus 0, 8. Okay. So now you can easily guess that the voltage would be what? 8 plus, it is falling from 1 to 0. So I can write this as 1 minus 0 into e power minus t by tau, right? Which is 8 plus e power minus t by tau is 5 by 9. So minus t by 5 by 9, which gives you 8 plus e power minus 9 by 5 t. Okay. 9 by 5 is 1.8, which means e plus e power minus 1.8 t volts. Okay. This is your V of t. Okay, simple, right? You need not solve the entire expression. Just find out the steady state voltages, find out the time constant from the Thevenin resistance, and apply some logic. Where is the voltage going from? You observe the circuit, observe the values. Where is the voltage going from? Okay, so there is a fixed component of 8 volts, and over that, I have a decaying component. Okay, yeah. Any doubt here?
No, sir.
Okay, great. So the answer would be, I think, option A, right? 8 plus e power minus 1.8. Okay, so if this is fine, we will go ahead with the next question. Yeah. So as I told, one question was on just the circuit. The next question is on the power factor, active power, reactive power, and so on. Okay. And there is a very interesting component over here, which is part number 4. We will see. Okay. That's why I have taken this particular example. Okay. So the question is an AC motor with impedance ZL is equal to 2 plus J11 ohms is supplied by a single phase 220 volts 50 hertz DC sinusoidal source. Find the power factor of the circuit, magnitude of current drawn by the motor, active power, reactive power, and apparent power, and determine the capacitor required to be connected in parallel with the motor so that the power factor is corrected to unity. Okay, so we will see one by one. Okay. Okay, so the first question is find out the power factor. So this should be very simple for us. We have already done something like this enough number of times. So you have your ZL is equal to 2 plus 11 ohms. Okay, so find out what is mod ZL, which would be root over 2 square plus 11 square. All right, so what is that? So you get somewhere around 11.18 ohms. Okay. But what about the theta or the phase angle, right? So your phase angle is basically tan inverse imaginary part by real part. Okay. So tan inverse 11 by 2, which is tan inverse 5.5. So this gives you 79.70 degree. Okay, 79.7 degrees the phase angle. So from this you can find out what is your power factor. So power factor is basically cos phi, that is cos 79.7, which is 0.179. 0.179, of course it is lagging. It's a motor load. Obviously it would be lagging, but yeah, 0.179. Yeah, so option A. This is pretty simple. Just resolve the um, given ZL impedance into its polar form. You will be getting. Okay. Okay. So this is fine, I guess. The next question is find out the magnitude of current drawn by the motor. Okay. So simple. We know what is mod ZL from the previous slide only. We saw it is 11.18 ohms. Okay. And they have given that the source supply VRMS. Okay. It's a single phase supply. And since they have given only the number, you should take it as RMS. Only if they give 220 sine omega t, then 220 refers to the peak value. Okay, but only if they give 220 volts, it refers to the RMS value. Okay, note this. Okay, so they have given VRMS, they have given ZL, therefore you very easily can find out what is IRMS, right? IRMS would be what? VRMS by ZL, all right? So 220 divided by 11.18. How much do you get? So I'm getting 19.68. Yeah, so 19.67 amperes. All right. So I think this is also pretty simple. Okay. Okay. So I think this is fine. So the next question is, and is okay. So find out the active power, reactive power, and the apparent power. Okay. So again, I would tell it's a very simple question. We know what is phi. From that, we can find out everything, right? And it's a single phase. So there is no problem for multiplication by root 3 and all. Okay. So what is the power? Real power. Real power is going to be VRMS, IRMS, cos phi. Okay. So VRMS is 220 volts and we calculated IRMS is 19.68. Correct. 19.68 and cos 5 in the first slide we saw it is 0.179. Correct. Cos 5 is 0.179. So into 0.179. Right. So this gives us how much? Gives us 774, 775 watts. Okay. I think the answer is B probably, but we'll just find out because there is an option called none of the above. Okay. So P is this, and obviously Q is VR, IR, sin phi. All right. So now cos phi is 0.179. All right. So sin phi would be how much? Cos square theta plus sin square theta is 1. So sin phi is root over 1 minus cos square phi. Okay. Or we also know what is the angle previously 79.7. So sine 79.7 would give you 0.983. All right. So 984. Okay. So this is 0.984. So 220 into 19.68 into 0.984. Okay. Yeah. So I'm getting 4259.83 VAR. Okay. And finally, S is what? VR into IR. Or if you want to take the long method, you can always do it as S is basically what? P plus JQ, right? So this would be P square plus Q square root over. So either way, 220 into 19.68, which you would be getting as 4329.6. Okay, so I think the option is B, right? 774 watts, then 4259 VAR and 4329.6 VA. Okay, again, pretty simple VI cos phi, and it's a single phase, so easy peasy. Okay, the final question is the interesting part. So the question is determine the capacitor required to be connected in parallel with the motor so that the power factor is corrected to unity. All right. So point is you have a load which is you are having ZL is equal to 2 plus J11. Right. The question is can I make ZL to be purely resistive? That is, can I make ZL to be resistive circuit so that the overall power factor is unity? Right. That is, can I have an element that will allow me to cancel out this J11?
Okay, so obviously you understand that since it is plus J11, I need to have something, I need to include something that would give me a minus J11, right? If I can add something that will give me minus J11, you will get the total impedance to be how much? 2 ohms. Okay, J11 and minus J11 would cancel out. Okay, so you can understand that XL is J omega L, which is a positive reactance. So whereas XC is what? 1 by J omega C or minus J by omega C. So you get this minus J term with a capacitor, right? This is with a capacitor. Okay. Whereas the plus term, right? Whereas the XL term is plus J omega L, which denotes the inductor. Okay, in this case, motor is made up of windings only, so basically it gives an inductive characteristic. Okay, right. So the question is, I will obviously attach a capacitor. Why? I will attach a capacitor so that I am able to compensate for this reactance. Okay, I am able to compensate for this inductance. Now, how to attach the capacitor, right? Here, for the sake of explanation, I have just added 2 plus J11 minus J11, but this is not how it works. They have told that if everything is connected in series, right? If you have a circuit that is connected in series, so you have R, you have an L, and let's say I put a capacitor over here, then the overall impedance would be how much? R plus JXL minus JXC, right? So I can directly write 2 plus J11 minus J11. But the question is not how is it, whether it's connected in series. The question is it is connected in parallel. Okay, so I cannot write straightforward that, okay, 2 plus J11 minus J11. It's incorrect, right? It is connected in parallel, which means that you can visualize the circuit to be something like you have R, you have L, okay, and they are adding a capacitor in parallel, which means that I will be having a capacitor like this. Okay, so I am having a capacitor like this. All right, now the point is they are asking what should be the value of the capacitor, so that if I see from here, right, if I see from here, I should see a net resistor. Okay, so they are asking what should be the capacitor value, so that if I observe from here, Z is purely resistive. Okay, Z should be resistive. It doesn't mean that the resistance answer would be 2 ohms. It means that what value of capacitor should I put in parallel so that I see an equivalent of a resistor. Okay, this capacitor should compensate the reactive part. Do you understand this problem? That is, what capacitor should I put so that this R plus j omega L, the j omega L part can be compensated. It is not that 2 plus j11, I will put minus j11. No, you are not putting a capacitor in series. You are putting a capacitor in parallel. So it is not that straightforward that, okay, 2 plus j11 minus j11. No, it's not like that. So do you understand the question?
Yes, sir.
Okay. Okay, great. So how do we solve this? So one thing is that, see, in parallel, right? So now we have put a capacitor in parallel. All right. So um, let me take a new slide. Oh, sorry. Okay. So let's draw the circuit now. That is, you have um, 2 ohms and then you have J11. I have put a capacitor over here. All right. Where is this eventually connected to? This is eventually connected to the supply. Okay. So this is my 1 by JXE, right? And of course, we told that it is connected to the supply, which means that I am giving 220 volts. Of course, it's a RMS single phase. All right. So now the point is the total current, right? Total current, if I call this as IL, right? That is line current is IL, it gets split into two components. Okay. So, okay, let me call this as I, not IL. It can be confusing. Okay. So let me call this as I. So it gets split into two components. One is through the motor IM and one is through the capacitor IC, right? That is your I is equal to IM plus IC. Okay. So we know what is IM. What is IM? IM is basically V divided by 2 plus J11. Correct? That is 220 divided by 2 plus J11. Right? So this is our IM. Correct? So yeah, this is what we did earlier also, right? That is, we found out the magnitude of current drawn by the motor alone. 220 divided by 11.18, 19.68 amperes. The angle is 79.7. Okay. So 19.68 and 79.7. So 19.68 and okay. This is one way of writing. Or let's put in some extra effort. Okay. So let's solve this. Let's simplify this instead of writing directly in polar form, right? So let's convert this into rectangular form. Okay. So 19.68 minus 79.7. How can we write it? We can write it at 19.68 into cos 79.7 plus j sine 79.7. Correct? Which means that this is in rectangular form, right? So 19.68 into cos 79.7 gives you 3.519, or let me simplify. So 3.52 plus j 19.68 into sine 79.7 plus j 19.36 ampere. Agreed? This is your IM. Okay. Is this agreed? This is fine. We have just converted whatever we knew, right? 19.68, we already computed the value in a previous question, right? Directly, I am writing the polar form to rectangular form. A into cos theta plus j sin theta. Is this fine?
Yes, sir.
Okay. So now the question is, how do I use the capacitor so that I can compensate this? Correct? We already told in the previous slide that I want to see a resistive impedance, right? I want to see a resistive impedance, which means that the current drawn, right? The total current I should not be having any imaginary part. Okay. So if total or net impedance is resistive, right? That is, if the capacitor is properly able to compensate, then if the total impedance is resistive, then there will not be any imaginary component, right, in current I. Okay, which means that if IM is drawing 3.52 plus J 19.36, IC would be minus J 19.36. Okay, so sorry. Yeah, so it means that if IM is 3.52 plus J 19.36, it means that IC would be negative of that, so that this imaginary part is getting cancelled out. Okay, so it means that so what does it mean? It means that your imaginary part will be 0. That is, since therefore I can write, since IM is 3.52 plus J 19.36 amperes, IC is equal to minus J 19.36. Okay, so that your total current I would be IM plus IC, that is 3.52 plus J 19.36 minus J 19.36, which would give you 3.52 amperes, right? So this is purely resistive. Did you understand this concept? This is how you should define this is how you should design the capacitor. Did you understand? The capacitor should be designed so that whatever current the motor is drawing, whatever reactive current, the lagging current that motor is drawing, my capacitor should be able to supply that current, so that my net uh, current drawn from the source is purely resistive. Okay, are you understanding?
Yes, sir.
Okay, so now what is this negative part signifying, right? We will calculate the capacitor and all, that's fine, but what is the negative part signifying, right? So generally itself, we see the convention that we have considered, right? That is, IC is entering over here. So current that is entering the capacitor is considered to be positive. Current that is entering the motor, that is considered to be positive. So if you see that the current that is entering the capacitor is negative, it means that the capacitor is supplying current, right? So basically the reactive component of current is being supplied by the capacitor to the motor. Okay. So this reactive part circulates only between this. It will not go to the supply. Okay. So that is what the sign is signifying over here. Okay. Okay. So we know what is IC. Let's calculate what is C, right? Um, yeah. So let me take a new slide and so we just saw your IC is equal to how much? IC is basically J 19.36 amperes. This is the imaginary part that is supplied by the capacitor. Okay. Okay. So you know IC is equal to what? V by XC, right? Or V by 1 by J omega C, right? Or J omega C into V. That is your I. Okay. So this is 1 and this is 2. Therefore, you can compare both of these. So 19.36 is equal to what? Omega into C into V. V is 220 volts AC. Okay. So 19.36 is equal to omega is equal to 2 pi into F, right? So 2 pi into 50, which is 100 pi. 100 pi into C into 220. Okay, just compute how much you are getting. So 19. Yeah, so I am getting 280.11 microfarad. Okay. So are we? Yeah, so 280 microfarad is the correct answer. Did you understand this? We have put a resistor in, we have put a capacitor in parallel so that the overall impedance is resistive. Okay, it doesn't mean that okay, ZL is equal to 2 plus J11, then I will add minus J11. Read the question very carefully. They have put a capacitor in parallel, not in series. If it was in series, you can tell okay, 2 plus J11 minus J11, right? But it is in parallel, which means that it is not straightforward. You find out the current is basically getting divided into the motor and into the capacitor, right? Into the motor and into the capacitor. So whatever reactive part is there in the motor, that is being supplied by the capacitor. All right. I think there is a sign mistake over here. That is, this is minus 79.7, which means that this would be negative, not positive, right? So this would be negative. So this is again negative. Okay. So this would be positive and this would be negative. All right. Yeah, now it is correct. Okay. Did you understand? Now we know what is I. The reactive part is being supplied by the capacitor. So you know what is IC, just the reactive term alone. So I is equal to what? V by XC or V by 1 by j omega C, right? That is j omega C into V, right? So you just, with the known quantities itself, you can find out. Okay. C turns out to, so if you put a capacitance of 280.11 microfarad, the net impedance becomes resistive. Therefore, you will be drawing a unity power factor current. Okay. So now your circuit is 2J11 and you have a capacitor over here. Okay. The capacitance value is 280 microfarad. This is your overall circuit. And what is the equivalent resistance? Can you tell? What is the R equivalent? R equivalent is not 2. Okay, R equivalent is not 2. R equivalent now needs to be calculated. That is 220 volts divided by what is the equivalent Z. Okay. Sorry, what is the, yeah, what is the equivalent current, right? Just the real part of the current. Okay. So what is the current? 3.52 minus J 19.36 and IC is plus J 19.36. So total current is 3.52 amperes. Okay, this is the current that is drawn from the supply. Okay, so that it is purely resistive. So total current is 3.52 amperes. Therefore, the answer is 220 divided by 3.52, which will give you how much? 62.5 ohms. You see the equivalent resistance that the circuit sees is totally different. It is not 2 ohms. Okay, now the equivalent resistance is 62.5 ohms because we have added this capacitance, right? You have to now consider the overall network and then calculate. Okay, so the R equivalent is what? 220 volts divided by the real part of the current because now the total current is purely resistive. That is only 3.52 ampere, no reactive part is there. Minus J 19.36 and plus J 19.36 have got cancelled out. Okay, so yeah, you calculate the current, motor current. So the reactive part will be compensated by the capacitor and well, capacitance is 1 by JXC. So using that, you can find out what is the capacitance value. So if you put 280 microfarad, you will be drawing a resistive current. Did you understand this question? It's a very important question, I would tell. Okay. Any doubt in this question?
No, sir.
Okay, great. Okay, so then we'll just go ahead. Okay. So the next question is, a simple diode rectifier has ripples in the output wave which make it unsuitable as a DC source. To overcome this, one can use dash capacitor in series with load resistance, capacitor in parallel with load resistance. Both of the mentioned situations will work and none of the mentioned situations will work. So what is the answer for this? So I have a diode bridge rectifier. Okay. So you know that if the input voltage is something like this, the output voltage that I would be seeing over here, right? The output voltage would be something like, agree? Is this fine?
Yes, sir.
Now the question is, what should I add after this terminal? After this blue terminal, what should I add? Capacitor in series with load resistance or capacitor in parallel with load resistance? And why
Capacitor
capacitor?
in parallel.
Why?
Capacitor in parallel.
Hmm.
Because it is smooth the waveform.
Correct. So basically capacitor opposes change in voltage. So if you design your capacitance properly and add a proper capacitor, what you would see is, right? So what you would see is that, so this is your profile, right? So what you would see is initially the capacitor would charge, it would charge up till this point, till the peak, and it would not fall down, right? So what would happen? The capacitor will very slowly discharge, right? It would discharge very slowly considering the internal resistance of the capacitor. And then again it would charge only till the peak and it will discharge very slowly. Okay, so the profile under steady state would look something like this. Okay, and if you add more and more capacitor, if capacitance value increases, if capacitance value increases, what you would be seeing is the profile would be more and more flat. Okay, so you'd be seeing something like, okay, almost flat. You get it right? So
Yes, sir.
higher the value of capacitance, the flatter it would be.
Yes, sir.
Okay. Fine. A capacitor in parallel to the load resistance. Yeah. So I forgot to add the load resistance. Okay. Fine. So we'll go ahead with the next question.
Okay, sir.
In the center tap circuit shown in the following figure, the diodes are assumed to be ideal, right? That is having zero internal resistance. Find the peak inverse voltage. So don't get bogged down by what is the definition of peak inverse voltage. Just find out what is the voltage the diode would be blocking, right? Peak inverse voltage means what is the voltage the diode would be blocking when it is off. Okay. So only if you know this answer, you can properly buy a diode. So let's say you have multiple options over here. Let's say my peak inverse voltage is 100 volts. That means that you have to buy a diode which is more than rated for more than 100 volts. So that's why people have to calculate what is the peak inverse voltage in the first place. All right. Okay. So 230 volts. Obviously, this is RMS, you know by now. Correct. And what is happening? It's a 5:1 transformer over here. So 230 gets stepped down into what? 230 by 5, right? Which is how much? So 46 volts, correct? Okay. So your V primary is 230 volts. Therefore, V secondary is 230 by 5, which is 46 volts. All right. Okay. So this is all. We are still in RMS. Okay. To find out the peak inverse, you have to, of course, go for the peak voltage. Okay, so we will do that later, but yeah. So V secondary is 46 volts. All right. Fine.
Yes, sir.
Okay. So now let's consider a scenario. All right. So in the middle, you are having 0. Okay. So in the middle, you are having 0 volts. Okay. And therefore, this should be minus Vm and this would be plus Vm. You are having 0 in the middle. All right. Okay.
Okay, sir.
So the point is, if I draw the circuit for, let's say, the top diode, okay, so I will be having a sinusoidal voltage over here, which is 46 volts, and I have a diode, okay, I have a diode, I have a ground over here. Let me redraw this. The same thing I am having minus 46 volts over here, and I have another diode, and both of these terminals get connected, and you have a resistance. Okay. Now you can understand easily that at one point of time only one of these would be conducting, right? That is, during the positive half cycle, D1 would be turned on, right? And during negative half cycle, the other one would be turned on. D2 would be turned on. Okay. So let's assume that D1 is right now off. Okay. We have to find out what is the voltage between cathode to anode that has made the diode off. Okay. Fine. So just take the anode side. Hmm. What is anode with respect to the ground? With respect to the ground, the anode is simply 46 volts RMS. All right. And I should tell minus 46 volts because we are taking the negative half cycle. Okay. So during negative half cycle. Okay. VA is minus 46 volts. And what is VK? What is VK? VK. Okay. So just one correction that we need to make is, okay, so V secondary, that is 46 volts, is across the entire transformer. So across the entire transformer, you are getting 46 volts, which means that individually it is getting split into 23 volts and 23 volts. Did you understand this?
Yes, sir.
So this is not exactly 46 and 46. I will um, redraw this and I will write This is 23 and 23. This is 23 and 23 because V secondaries across the entire secondary winding, we are getting 46 volts. We are physically tapping from the midpoint. Okay, that is our connection. So the entire winding spans from top to bottom. Okay, so V secondary is 46 volts. So individually between the center tap, you get 23 and 23, which means the total voltage is 46. Okay, so we have to make this correction over here as well. Okay, so yeah, so this is during the positive cycle. Let's see this. So during the positive cycle, right? During the positive cycle, your VA is going to be how much? During positive cycle, diode D1 would be on, D2 would be off. So let's calculate for D2. You have anode here and cathode here. And let me erase this. Okay, so we have anode here and cathode here. All right. So what is the anode voltage? Anode voltage is minus 23 volts RMS. And what is the cathode voltage? The cathode voltage you can trace back from here, right? Same point, same point, same point. This diode is on. So you come over here, you come to this point, all right, which is 23 volts. Did you understand how we wrote VA and VK?
Yes, sir.
Okay. So now your VKA, right? Cathode to anode voltage can be written as 23 minus of minus 23, which is 46 volts RMS, right? Or 46 root 2 is the peak, right? So 46 root 2 gives you 65.05 volts. Okay. Yeah, so don't make this.
Root 2 where comes, sir?
So yeah, so they have asked for the peak inverse voltage, right? Peak value.
Yes, sir.
Right
Yes,
now
sir.
we are still dealing with RMS. They have told 230 volts means it's RMS. So we converted it to the other side. We are 46 volts. 46 volts is RMS, right? So VA, when we tell 23 volts, that is 46 volts getting split into 23 and 23, right? So VA 23 volts RMS, VK 23 volts RMS. All right. They have
Yes,
asked for
sir.
the peak inverse voltage. So the diode should be rated for obviously the peak voltage, peak of the sine wave, right? It cannot be rated for some RMS value, right? So that is why we have taken for this is 46 volts RMS for to find out VKA peak, right? We have to, they have asked for the peak inverse voltage. So that's why 46 root 2. Okay.
Yes, sir.
So 65.05, which is option C. Okay. So one thing I will just clarify that even though it's a center tab, even though the transformer is center tap, V secondary 46 volts appears across the entire secondary winding. Secondary winding. Okay. So this is something we need to make note of, remember. Okay. That is why individually it will get split into 23 and 23. Okay. Individually it gets split. Individually we get V secondary by 2. Okay. So I hope this clears the whatever confusion we were having. Okay.
Yes,
And
sir.
you take any particular half cycle. So during positive half cycle, this is during positive cycle. So if you took the negative half cycle, it would just be minus 23 volts and minus 23 volts. At that time, the top diode would be off, bottom diode would be on. You do the same analysis, you will again get 46 volts RMS, 65 volts peak. peak inverse voltage is 65. Simple, right?
Yes, sir. Clear.
Okay. So see, generally for ease of values, I have just did with RMS itself. Generally, while doing this peak inverse voltage calculation, first people would convert this into peak value. So 230, you write it as 230 root 2, 46, 46 root 2. So 23 root 2, 23 root 2, and so on. Right now, I didn't want to have those root 2 terms additionally right now. So that's why I finally included the root 2 term in the last step. But generally, while solving problems, people also have a practice of including root 2 in the start itself. Okay, but for our ease, I have not considered that. But anyway, you remember that in the last step, you have to include that root 2 term because the question is peak inverse voltage. Obviously, the diode would be blocking the peak voltage, right? The diode cannot be rated for lower voltage. So you have to consider the peak. Okay. I think it is now clear. Uh, Next question is again simple. Yeah, yeah, thanks. So the next question is again simple. The bridge rectifier shown in figure uses silicon diodes. Okay, take a drop of 0.7 volts each, right? If you tell 0.7 volts drop, that is VAK is 0.7 volts. Okay, so find the DC output current. All right. So they have told this is 12 volts AC rated. They haven't given any turns ratio, so assume it's a 1:1 transformer. So you give 12 volts here, you get 12 volts here. Okay, assume it's a 1:1 transformer. Okay, so 12 volts AC means it's obviously 12 volts RMS. Okay.
Okay, sir.
Fine. Fine. Okay. Yeah. So in a full bridge rectifier, in a full bridge rectifier, what is the output voltage? Average output voltage, V naught average. Do you know? It is 2 Vm by pi. Okay. So where Vm is the peak voltage, V max, 2 into 12 is the RMS, therefore 2 into 12 root 2 by pi. Okay. Um, Therefore the voltage is how much? 2 into 12 root 2 by pi. So you get somewhere around 10.8. Sorry, 10.804 volts. This is the average output voltage. Okay. They have asked for the average output current, I naught average. I naught average would be how much? V naught average divided by your RL, which is 10.804 divided by 12K. So divided by 12K. Around 0.9 amperes. Okay. So now let's see the circuit once. See the options. Is there any option of 0.9 ampere? No. So why what is the mistake that we did? The formula is all correct only, but what is the mistake that we did? What did we not consider? See, in a full bridge rectifier, ideal full bridge rectifier, okay, in an ideal full bridge rectifier, the output voltage is 2 Vm by pi. Okay. If you tell ideal full bridge rectifier, it means that the diodes do not have any drop. Okay. In that case, you get output voltage 10.804 and divided by 12K, you will be getting 0.9. All right. Okay. But the point is right now they have told that the drop is 0.7 volts. Okay. From seeing the options, probably you may guess that the correct answer is 0.825, and I think it's the correct answer. Right, we have got 0.9. So if you consider the drop and all, the voltage would be slightly decreasing, which means that the current would also decrease a little. But we have to find it analytically. All right. Did you understand this?
Yes, sir.
Okay. So I will just done. Okay. So let's try to solve this. So I'll just add new slide. Okay. So let's try to understand, right? So V naught average is 2 Vm by pi. Now the point is Vm is 12 root 2. So 12 root 2 you are getting over here. 12 root 2 volts. Okay. But if you see the output, 12 root 2 is not exactly going to come. 12 root 2 is going to come with a drop. Right? 12 root 2 is going to come with some drop. Right? Okay. So can you tell if you know the operation of this DBR at any point of time, what will the diode conduction be? So let's take, you have something like this, and something like this. Okay. So D2, D3, D4, D1. All right. And this is where you're taking your output. Hmm. Hmm. Okay. So if so positive half cycle, during positive half cycle, right? So during positive half cycle, which diodes will be on? During positive half cycle. So positive half cycle means here you are getting positive. Okay. So if you get a positive voltage over here and you get a negative voltage over here, so which diode will be on? Obviously, D3 would be on. Would D2 be on? No. And D1 would be on because at the cathode you will be getting a negative voltage and here you are having zero. This is zero. This is negative, which means that D1 would be forward biased. So D3 and D1 are on, and during negative cycle, during the negative half cycle, so during the negative half cycle, obviously you can easily guess D2 and D4 are on. Okay. So at any point of time, two diodes are in conduction. All right, two diodes are in conduction at any point of time, which means that voltage drop would be how much? At any point of time, the voltage drop through the diode bridge rectifier is going to be how much? It is going to be 2 into 0.7 volts. Each diode has 0.7 volts drop. So voltage drop would be 2 into 0.7 volts, which is 1.4 volts at any point of time. Okay. Did you understand this?
Yes, sir.
So at any point of time, you have 1.4 volts drop, which means that over here, instead of applying Vm, we have to account for the drop, which means you cannot directly apply 12 root 2. The peak value would be now decreased by Vm, that is 12 root 2 minus 1.4. Okay, that is why now the voltage would be V0 would be 2 Vm dash by pi, where Vm dash is what? 2 into 12 root 2 minus the voltage drop, which is 1.4 divided by pi. Okay. So what is the voltage you would be getting? Well, account for the drop, right? Two diodes are in conduction, which is 2 into 0.7, 1.4 volts. So 12 root 2 minus 1.4, correct? So 12 root 2 minus 1.4, you get 15.57 into 2 by pi, which is 9.913 volts. Okay. Therefore, your I naught would be V naught by R, which is 9.913 divided by 12 kilo ohm, right? So you will be getting, I am getting 0.826 milliampere because it's a 12K kilo ohm. So 0.826 milliampere, which I think matches, right? 0.825 milliampere. Did you get it? Once you accounted for the drop, then you calculate the average value. 2 Vm by pi. Now it becomes 2 Vm dash by pi, where your Vm dash has to account for the drop. That is 12 root 2 is coming at the supply. Then you have a drop of 0.7 and 0.7 in two diodes that are in conduction, which means 12 root 2 minus 1.4, right? That is peak supply minus the drop. Okay. Yeah. So is this fine?
Yes, sir.
Great. So now we are done with these introductory problems. That is, we have seen two problems on the rectifiers, three problems on rectifiers. So one is this, including non-ideality, that is voltage drop across the diode, a non-ideal diode. And then we saw a problem on center tap rectifier and just a very basic problem. And then we saw this capacitive compensation, or we call this reactive compensation. So this capacitor, adding a capacitor in parallel that we saw sometime earlier, this concept is called reactive compensation and it is very widely employed. Okay, very widely employed. But you need to calculate, or you need to understand what is the value of the capacitor to be chosen. So if you know the motor parameters, that is 2 plus J11 ohms, right? If you know what are the motor parameters, in the motor, they will be giving you the resistance, motor resistance and the motor inductance, winding inductance. Okay. So if you know the motor resistance and motor winding inductance, the value would be R plus JXL. Now you have to design or put a capacitor so that the equivalent impedance is purely resistive. Okay, R equivalent. This R equivalent and the motor resistance will not be same once you put the capacitor, right? So you put a capacitor over here and just make sure that the total current drawn from the supply is resistive or has only the real part, no imaginary part, only real part. So the imaginary part of current is being supplied by the capacitor. Imaginary part is being supplied by the capacitor. So the imaginary part is like a circulating current within the motor capacitor loop. Imaginary part circulates only within over here. Only the real part is coming from the source. That is the advantage of putting a capacitive compensation. Okay, so you have to calculate the proper capacitance. We saw this, and yeah, and one was on basic circuits. That is, know what is the steady state value before switch closes, after switch closes, find out the tau, and try to think a little. Where is the voltage going? From where to where is my voltage going? Okay, what is the decaying component? And what is the fall of decaying component? Right? Is it going from 20 volts to 8 volts, 9 volts to 8 volts? In that case, what is the decaying component? Okay, simple. It's very simple if you do it like this. Okay. Okay, so we will go ahead with problems on two-port networks. Okay, so just give me a break for 3 to 4 minutes. I will have some water and then we will resume. Right?
Okay, sir.
Okay, so we will resume. So before we go ahead with the problems, right? So we will just have a cheat code or cheat sheet, right? So we can uh, easily come back to this at any point of time, okay? Instead of just mugging up or memorizing the formulas. There are simple ways. Okay, just we will just note down what we know so far, and with that piece of information, we will try to go. Okay. Okay. So yeah. Right. So one thing that you would know, right? We will start with what we know. Okay. So V is equal to impedance matrix Z into I, right? So you can easily double guess that. Okay, okay. So V1, V2 would be what? Z11, Z12, Z21, Z22 into I1, I2. V is equal to I Z into I. Very simple. All right. And just like superposition theorem, if you want to find out Z12, for instance, right, it would be simply V1 by I2 with I1 equal to 0. Simple, right? So you have to disable the other source. So this is the impedance matrix. Impedance matrix. So the next thing that we would require is obviously your admittance matrix, which is your I is equal to Y into V. So I1, I2 is equal to Y11, Y12, Y21, Y22, V1, V2. So this is your admittance matrix. Okay. And something we are all aware of, right, is that Z is equal to Y inverse. Just take the matrix inverse of Y, or same Y is equal to Z inverse. Okay, both of these are just inverses. So you got what is the impedance matrix and you got what is the admittance matrix. All right. So as an extension, all right, as an extension, you are having the next one, which is your transmission line matrix, wherein if you have a two-port network, right? So I will call this V1, I1. So port 1, or let's erase this. We will write it in the simpler form instead of just V1, I1, right? So I will write it as port 1 parameters is equal to what? Is equal to the transmission line parameters, transmission line into port 2 parameters. So we have port 1, and then that can be written as some transmission line matrix into the port 2 parameters. So what we really mean over here, so you can understand V1, I1, that is current leaving port 1 is equal to transmission line parameters, which can be called A, B, C, D, into port 2 parameters, which is V2 and minus I2. Okay. And why is the minus sign coming? Can you tell why minus sign is coming?
Sir, maybe due to the opposite direction of the source current, it is the load current. That's why.
Correct, correct. So the idea is that Yes. So you are having port 1, P1, let's call it, and you have a transmission line in between. Okay. And then you are having port 2. So if I erase this, you are having the matrix over here. So this is V1, this is I1. Okay. And this is V2 and this is I2. Right. So you can see that the direction of current in port 1 is entering and in port 2 it is exiting. Right. Or whatever convention you take. So the direction of current is opposite with respect to the port. That is why we have V1 I1 is equal to ABCD V2 minus I2. So do not neglect this negative sign. Okay. So we have the transmission line parameters. So far so good. Simple. We have related the admittance, impedance, and the transmission line. That is, port 1 is equal to some factor into port 2. Okay, just a cascade, right? Now we will go to the cross parameters, which are the H parameters and the G parameters. So as far as the H parameters are concerned, take the cross. Okay, H parameter is V1, I2 is equal to H11, H12, H21, H22 into I1 V2. Okay, so of course, if you tell H11 would be V1 by I1 with V2 equal to 0, which means if V2 equal to 0 means the voltage source V2 is shorted. Okay, so that is something we have to keep in mind. So V1 by I1 with what? V1 by I1 under what condition? V1 by I1 under V2 equal to 0. So these are the H parameters. And complementary, we have the G parameters, wherein you have I1 V2 is equal to G11, G12, G21, G22 into P1 I2. So these are your G parameters. Okay. So we will be solving problems on these mostly. Okay. Okay. So the first question. So before we go ahead, you can easily double guess that since it's an impedance matrix, all the entries will be having the unit ohm. All the entries will be having the unit ohm. Since this is an admittance matrix, you will be having 1 by ohm, which is Siemens or capital S as the unit. Okay. For individually, for A, B, C, D, and for H parameters and G parameters, individually the unit will differ. The unit can also be dimensionless. If it is V1 by V2, right? H12 is what? H12 is V1 by V2. H12 is basically dimensionless, right? So H11 is equal to V1 by I1 with V2 equal to 0, right? Which means it is going to be in ohms. If you see H12 is going to be V1 by V2 with I1 equal to 0. So it's a voltage ratio, right? Voltage ratio is dimensionless. So you have parameters which can be dimensionless as well, without any dimension, without any unit. So that case arises for transmission line parameters and the H parameters and G parameters. So some transmission line parameters H and G parameters can be dimensionless or dimensionless. So don't be afraid that, oh, there is no dimension over here. I should have done something wrong. So point is, you remember this, that some parameters can even be dimensionless. Okay. So let's go ahead. Yeah, you see all the options over here. This is having Siemens, then no unit over here, and then you have ohms. Okay, so yeah, you take care of the unit. All right. Okay. So the first question is, they have given the transmission line parameter T, right? T is equal to 10, 1.5 ohm, 2S and 4. That is A, B, C, D. A, B, C, D is basically 10, 1.5 ohms, 2S and 4. All right. Find the G. Okay, they have given the T parameters. Find the G matrix, right? G matrix means the relation I1, V2, V1, I2 relation. Okay. Okay. So transmission line is, you remember transmission line means something like a cascade. That is port 1 is there. Port 1 is equal to something into port 2. So V1 I1 is equal to ABCD into V2 I2. V2 minus I2, right? So you just immediately it should strike in your mind. If it's transmission line, then port 1, port 2. So V1 I1 is equal to ABCD into V2 minus I2. All right. So that should be the first thing that strikes in your mind. All right. Okay. So we will write this as V1 I1 is equal to ABCD into V2 minus I2. Okay. All right. Which means that if I can expand this, I will be getting V1 is equal to AV2 minus BI2 and I1 is equal to CV2 minus DI2. Okay. Keep this on one hand. Okay. Let's go to what we know about G parameters. All right. So this is one, that is the transmission line parameters. The other thing that we know is the G parameters, right? So what are the G parameters? G parameter is I1 V2. Yeah. Okay. So I'm just expanding this, all right? Okay. So we are having the second equation. So you see over here, that is V1 is equal to AV2 minus BI2, I1 is equal to CV2 minus DI2, and similarly we have expression for I1 and V2 in terms of G parameters. Now if we can solve this, we know what is ABCD, we just need to solve it properly and we will be getting the answer. Okay. So how do we solve this, right? That is the question. That is, how do we solve this? Okay. Just hang on a second. I will just slide. Okay. Yeah, okay. So we have written it correctly. I just wanted to check if we wrote the expressions for G parameters correct. Okay, so we are fine over here. Okay, so what did we write? V1 is equal to A V2 minus B I2, right? And I1 is equal to C V2 minus D I2. Okay, this is from the ABCD parameters. And you have um, I1 is equal to G11 V1 plus G12 I2. And V2 is equal to G21 V1 plus G22 I2. Okay, so these are the two expressions. All right. Now I want to find out the G parameters, right? So I have to substitute from 1 into 2. Okay, fine. So what happens to I1 now? Into I1 now becomes I1 is equal to G11 V1 plus G12 I2, right? Which means G11 into V1 is AV2 minus BI2 plus G12 I2. Okay, that is G11 AV2 minus G11 BI2 plus G12 I2. Okay. All right. So this is one. Next is okay. So um, okay. So let me get rid of this for now. And what I will do is to make things simpler, I will go in one. And what is V1? V1 is equal to A V2 minus BI2, which means that my V2 is equal to V1 plus BI2 by A. Correct? This is my 3. So this is V2. V2 is equal to V1 plus BI2 by A. Okay. So This I will put in I1 expression. I1 is equal to what? CV2 minus DI2. All right. So C into V2 is V1 plus VI2 by A minus DI2. Okay. I1 is basically then C by A V1 and then plus CB by A minus D into I2. Okay. So compare 4 and 3A. See, I1 is C by A V1 plus CB minus A minus D, CB by A minus D I2, right? So this is like telling I1 is equal to G11 V1 plus G12 I2, right? So you get G11 is equal to C by A, G12 is equal to CB by A minus D. Okay. So C by A is what? C by A is 2 by 10, 1 by 5, and CB minus A by CB by A minus D, right? So we have to do a bit of computation. Um, I am getting minus 3.7. So did you understand what we were doing? So I know the expression for the transmission parameters. That is, I know what is ABCD, how it is related to V1 I1 and V2 I2. And I also know what is G parameter, right? That is I1 V2 is equal to G into V1 I2. Okay. So from this, what I did, I was trying to get the transmission line expressions in terms of my G expressions. Okay. So see in the G expression, there is no V2 on the right hand side, right? So there is no V2 on the right hand side. There is only V1 I2 and V1 I2. So there is no V2. So no V2 and no I1. Okay. So no V2, no I1, which means that you can eliminate V2 and I1. That is why we found out what is V2, right? We found out what is V2 and we have eliminated V2, right? We eliminate V2. Eliminate the parameter which is not there in the final expression. So you get an expression in which there is resemblance to the in which there is resemblance to the G parameter expression. Okay. Did you understand this? It's a bit of some math, some playing around with it. But point is, you identify what parameter is not there in the final expression. See, on the right hand side, there is no V1, there is no V2, there is no I1. So you eliminate V2 and I1. Okay. Similarly, also V1 is equal to A V1 minus B I2 and I1 is equal to C V2 minus D I2. But over here, this is from the transmission line parameters. But in terms of the G parameters, I have G11 V1 plus G12 I2. And similarly, we have V2 is equal to G21 V1 plus G22 I2, right? So see over here that on the right hand side, there is no V2, no I1. So what you should do, the first step you will take is eliminate V2 and I1. Okay. That is what we will do. Eliminate V2 and I1. right? That is why what we did was we found out what is V2 and substituted it in the I1 expression and we kind of equated it. All right. Okay, so we will continue. That is V2 from this particular expression, right? So V2 is equal to what? 1 by A V1 plus B by A I2, right? So you can understand, you compare this and this, you understand that G21 is equal to 1 by A and G22 is equal to B by A. Okay. So 1 by A is what? 1 by A is basically 10. So 1 by 10, which is 0.1, and B by A, B is 1.5. So 1.5 by 10, which is 0.15. So your final G matrix, right? So final G matrix is going to be G11, G12, G21, G2. Okay. So G11 is 0.2. And then G12 is minus 3.7. And this is 0.1 and 0.15. Yeah, this is the correct answer. Did you understand how we did it? That is, you have to write your given expression into the form of expression that you want. Okay, basically you have to write these expressions into the expression that you want. Okay, that is the way to solve. Did you understand it?
Yes, sir.
Great. So we have time for one more problem. So this is a very simple problem. So Z parameter is given. Z is given as 10, 5, 10 and 10. So how do you find Y? Basically, Z is equal to Y inverse, right? So or Y is equal to Z inverse, which means that you have to just take an inverse of this matrix to find out what is the Y matrix. Z is given, Y is basically Z inverse, right? So 1 by determinant. So what is determinant? 10 into 10, 100 minus 10 into 5 is 50, right? And then what is the matrix? The principal column elements will be 10 and 10. And what happens to, okay, so will be 1 by 10 and 1 by 10. And what happens to this? It will become minus 1 by 10 and minus 1 by 5, right? Correct? So you'll be getting 1 by 50 into 0.1, 0.1, and minus 0.1 and minus 0.2. Okay. Yeah, so okay, I think we did a mistake in this, right? So I think we have to kind of exchange the so these will get hmm. Yeah, I think over here
Sir,
there
sir,
is sorry.
sir,
Yeah.
cannot we use directly calculator to just find the Z inverse and mark the answer, sir?
Directly calculate as in like
Sir, can we not use the directly scientific calculator to find the inverse of Z and then mark the answer, sir?
Yeah, you can very well do that. Yeah.
Yes, sir.
Yeah, sure. I think I did a mistake over here somewhere. Was just trying to do it. I think that would be correct. So okay, so just hang on a second. I will just delete it. Yeah, so how do you find y is equal to z inverse, which means we have 1 by mod z, and then the entries kind of get interchanged, right? That is this will be z11, this will be z22, right? And this will be minus z21, this will be minus z12, correct? Yeah. So this is basically 1 by determinant of z is what? So 10 into 10 minus 10 into 5, right? So that is so this is basically 1 by 100, 1 by 100 minus 50, and z11 is still 10. This is sorry, yeah. So this is 1 by 100 minus 50, and this is 10, this is 10. Okay, this would be
Minus 5 and the
minus
minus
5.
10. Minus 10.
Correct. So you would, yeah, I'm sorry, something's happening. 50. I don't know what's happening. As I write, it's getting erased. Oh. Ten, 10. All right. So 1 by. I don't know what's happening. Okay, so I think
No,
you get the idea.
no, it
So,
is, sir. Yes,
okay,
we
so
got it. That's what it said.
this is
The
the
answer will be
sentence.
last. Yes, sir.
Yeah. Anyway, okay, so then we will conclude for the day. I think we are past 8 o'clock. So yeah, thanks for
Yes, sir.
attending, and we will
Sir,
continue from the next session. Yeah.
yes, sir. Sir, actually, I missed the initial session because it is heavily raining here in Odisha, sir. So due to network issue, I
Okay.
just joined at 7:30, sir. So can you please
Okay.
upload the video in YouTube so that I can do it tonight, sir?
Sure. Okay.
Yes, sir. Thank you very much, sir. Thank you.
Yeah. Sure. Okay.
Good night, sir.
Good night. Good night.